So I'm starting recording and I'm sharing the screen.
Okay.
Now, can I start the session? Please inform me. So, can I start the session? Am I audible to all of you?
Professor Saurabh Kaur, please start the session. Please show your presentation.
Okay, will I start? Okay, so I'm starting, right? Okay. Good afternoon, everyone present here. Good afternoon, Suman madam, all the professors, HOD ma'am, and everyone, all the students present here today. So today I will be delivering a very small lecture on a very fantastic and very prominent topic nowadays as far as structural engineering is concerned. Not only we are concerned regarding the construction materials and technology, but also we are very much concerned regarding the performance of the building structures existing or to be constructed in the future years. So in association with Heritage Institute of Technology and TECHNO India University, Salt I am Professor Saurabh Kaur. I will be delivering a small lecture session. So this session, this topic is a very vast topic. It consists of two important aspects. You can see seismic analysis of tall structures and ductile detailing of RCC structures. So first of all, I will be basically focusing on the first topic, that is seismic analysis or earthquake analysis on tall structures. Now, before coming to the seismic analysis, I want to focus on what is tall structures or something like that. So wherever we are talking about tall structures, so the first question comes in our mind that which type of structure or what should be the height of the structure so that we can consider it as a tall structure. Because structures, according to the designers and architects all over the world, they are mainly classified as three basic types, even though that is subjective: low-rise structure, mid-rise, and tall structure, or high-rise structure. So as I told you, this tall structure or high-rise buildings, they do not have a particular definition as given in the code or some guidelines. It is very subjective. Actually, the tall structure or high-rise structure is dependent on the surrounding environment buildings or the height of the surrounding buildings existing nearby. If you talk about some basic definition or basic criteria, the National Building Code in the year 2005 defined high-rise building as a building with more than 15 meters or 5 stories. It was way back. You can see it was defined in 2005 and it is 2022. So over the last decade, this definition has changed and it has been updated to a height of, just a minute. So so now over the last 2 years, this definition have changed or advanced into that we can define a tall structure as having the height of the buildings more than around 50 meters or 60 meters. So now Even the Council on Tall Buildings and Urban Habitat, which is a foreign concern, a foreign organization, they defined the tall buildings as super tall, which is more than 300 meters. Even sometimes the super tall buildings have turned into mega tall buildings having height more than 600 meters. So if I take the height of a floor as 3 meters, so it is almost around 200 floors. So usually when the building or when the structure contains more than 100 or 150 floors, we consider it as tall structures or skyscrapers or high-rise buildings. So with the advent of these structures and design and construction, a very important concern or key important point comes into the picture. That is, along with the wind analysis or wind load, we also have to consider the seismic load or earthquake load. Now, we have Indian codes, IS 1893, 2002 version and 2019 version, which talks about seismic analysis. So these are some of the well-known and renowned structures all over the world. Now coming to the seismic or earthquake study. So before directly going into the scenario of how to find out or how to calculate the earthquake load, we have to first learn about what is the basis of earthquake engineering. So this basis of earthquake engineering lies on geology. The major tectonic plates of the Earth's surface, they are basically classified around 6 to 7 different plates. We have Eurasian plate, North American, Pacific, South American, African, Indo-Australian, and Antarctic plate. So our plate, the Indian subcontinent, lies on Indo-Australian plate. Now, what is the thing to be, what the main thing concerning this plate? Now, whenever this plate, there are different plates lying beneath the Earth's surface. So whenever this plate, they are colliding each other, either they can be in convergent or in divergent form. Whenever they are colliding each other, a huge amount of energy is released in form of elastic waves. So this huge amount of energy, which is developed beneath the Earth's surface, they are released in form of waves, which are basically technically called as elastic waves, and they causes excessive stresses in the Earth's surface. So due to this huge amount of waves, they result in some excitations or seismic excitations or seismic tremors. So these seismic tremors, they are also known as earthquake excitations or ground motion. Technically, they are also known as ground motion. So coming to the way, the pattern by which the tectonic plates, they collide each other, either they can be parallelly colliding, like they are somewhat like there are some slips. That is we can see the zone where the two plates, they are colliding each other, or there are some stresses generated at the interface. That is called slip or fault. This is called fault line. Sometimes we have convergent form of collision. We have transform boundary, like the two plates are parallelly, they are sliding each other in opposite directions, or sometimes divergent boundaries. So three types of boundaries or fault can take place. So we can talk about this. Most earthquakes in the world, they occur along the boundaries of tectonic plates. Like we have interplate earthquake, which was the result of Assam earthquake in 1897. Some fault took place where the plate boundaries collided each other face to face, which is called interplate earthquake. That was the result in 1992 earthquake. So coming to this, so these are the various types of slips. As I told you, there are many types of faults or slips that take place for earthquake tremors. As I told you, that this energy dissipation, the amount of energy is a huge amount of energy which is very much causes the earthquake waves and which acting on the structure. Now we can see elastic rebound theory, or we can see that the energy is basically in form of dynamic loading.
I would just intervene 1 second.
Earthquake,
Arun Kumar Chakravarti, please mute yourself.
ma'am, I can't hear you.
Yes. It's okay. You can carry on now.
Okay. So coming to this, so how the ground shakes. So after the dissipation of the energy, there is a ground tremors. So the ground tremors or the ground waves, they're also classified in different forms. Surface waves, some in body waves, which is acting on the surface of the earth or sometimes beneath the earth's surface. So we have mainly P waves and S waves. P waves, they are basically the body waves and surface waves. The body waves consist of primary waves and secondary waves, and the surface waves consist of Love and Rayleigh waves. So if we talk about the P waves, they are basically transmitted. They are transmitted in push-pull format. That means some zone is extending, but some zone is compressing. And while talking about S waves, they are side-to-side vibration taking place. We have also Love waves and Rayleigh waves. Compared to this, we can see, compared to all the four types of waves, Love waves, Rayleigh waves, S and P waves, the S waves is more disastrous. And as we know, the after effect of the ground excitation is complete collapse of property and loss of human life. Now, coming to the various seismic zones in India. The earthquake study took place in India after the 2002 Bhuj earthquake. After that earthquake, which had a Richter scale of around 8.9, the measurement or the scale of earthquake was 8.9 in the Richter scale. After that, IIT Roorkee, the earthquake division, along with various Indian government organizations, they have set up and they have organized an extensive study on earthquakes. So if we talk about how to find out the seismic measurement, or how to find out calculate the earthquake forces acting on the structure, first type code was IS 1893 Part 1 2002. This is the old code. Now we have the 2016 version, which is the new code. So this is if you can see, this is the front page. This is the IS 1893 Part 1 2016. So this is the latest code, which had some revisions based on the older code. So if you talk about some past earthquake which took place in India, these are based on the study. So how the study took place? The study took place based on a huge number of data obtained from the Indian Geological Survey of India, and over the data have been collected over last 100 years or 200 years. Based on the study, the date of the event, time, magnitude, area, and the amount of loss of life as well as property loss. Based on this study, the various seismic zones in India, they are classified into 4 main zones. We have zone 1 and zone 2. They are both considered as zone 2, zone 3, zone 4, and zone 5. So mainly as we approach or as we progress from zone 2 to zone 5, the intensity exceeds. Now, what is this zone 2, zone 3, and zone 4, all these things? Zone 2 is basically the areas which are plain land area. They are not hilly areas. So the zone or the areas which is plain land, they are less susceptible to earthquake damage. While if you talk about zone 3, it is slightly undulating area like plateau area, like Jamshedpur. If you talk about zone 4 and zone 5, these two zones, they are severe and very severe. They causes very severe damage. So this zone 4 and zone 5, if we see the code, mainly the hilly areas, mainly the mountainous area, they fall under zone 4 and zone 5. Along with this zone, we have zone factor value also, the Z value. So this value of Z, this will be required later on when we will learn the equivalent static analysis based on seismic analysis. Okay. So I will come to those formulas, but for time being, let us know that this zone factor, they have some value along with the various zones in India. So this is the map of various zones from zone 2 to zone 5 given in the older code. Now, coming to the how the mechanism or the structural dynamics acting behind this earthquake engineering. Mainly whenever we have ground motion or seismic excitation, it is acting on the structure. The structure, these waves or this vibration, they are transmitted throughout the building. Now, if we see that this is the equation, which is basically the equation for multiple degrees of freedom, MDOF. We have two types of degrees of freedom system. We have single degree of freedom system, SDOF, and multiple degrees of freedom, MDOF. Okay. Now, this is the force equation where we can see mx double dot. That means it is basically the force. The force is external force where x is the displacement, x dot is the velocity, that is the first order differentiation. X double dot is the second order differentiation, that is acceleration. So if we know MA, that is the mass into acceleration, plus what is the C? C is the damping coefficient, K is the spring constant, is the restoring force. So this is basically the multiple degrees of freedom equation. This is the most critical type of the equation or differential equation based on which structure vibrates. If we can see, we have, whenever we have this acceleration or this ground motion acting on the structure, there is some restoring force acting on the building. Okay, so based on this mechanism, we have this equation has been developed. Now, what is the various direction along which the seismic forces act? It can be in along, it basically, it is a lateral force. Just like wind load, earthquake load is also lateral force. That means it will act in horizontal plane. So if we take X and Z as a horizontal plane, so we can have forces in positive X direction, negative X direction, positive Z direction, and negative Z direction. So that means basically what we are having, we are basically, why I showed you in the positive X and negative X, that means we can have positive X means in the right side and negative X means in the left side. That means in the both the directions, in both the directions of in both the directions of the X and Z direction, the forces are acting. Similarly, this is how we put the loading or we impart the loading on the structure. When we model the structure in something finite element software like StatPro or ETABS or some sophisticated software. Now coming to this, so this is another pictorial representation. So how the inertial forces, that means the forces which is basically acting on the slab the walls and columns, and the foundation. So the foundation will be shaking in the direction of earthquake, while the beam, columns, and the slab, they will be subjected to initial forces in the opposite direction. The worst effect, we have seen a huge, the loss of hazardous effect takes place. I have taken some pictures from the BMTPC guidelines. The left corner diagram is the collapse of masonry structure. The right side is the collapse of the RCC, the structure which took place in Bhuj, which was in Gujarat. That 2001, it was took in the 2001 year, and after this earthquake, the Bhuj earthquake, the total picture of the earthquake study in India has changed. Now coming to what is the solution? So the solution is basically nothing but the performance-based design. So whatever design in our undergraduate level, what we have studied that all the design is taking place in elastic limit. That is, we undergo elastic design according with the IS CODAL provision, like IS 456/2000 or IS 800/2007, that is steel code. But nowadays, besides architectural and aesthetic point of view, we have to go for beyond the elastic limit. We have to design for inelastic loading also. So this is the advent of performance-based design. So what is performance-based design? It is a special type of design which is advanced level apart from normal traditional designing, which takes place into consideration of what will be the performance of the structure post earthquake. That means we will be able to visualize and what will be the type of failure or what will be the pattern of failure if a hazardous earthquake or hazardous some natural calamity will be taking place on the structure. So since today we are more focused on the seismic analysis, so today I will be discussing on earthquake forces. The main objective of earthquake engineering is to design earthquake resistant structures. There is nothing called non-earthquake design. The design is earthquake resistant structure. That means it has three philosophies. Again, coming back to the Indian IS CODAL provisions, we will have the main philosophy is that we have to design and we have to construct an earthquake resisting structure which will be able to minimize the loss of property and life whenever earthquake is hitting the structure. It is absolutely impossible to save the aesthetic properties like glass, facade, doors, windows. This property loss will not be able to be, we cannot curve this thing. But the main philosophy lies in this part that the total integral structural property should not fail. That means we will be able to design such structures which will be able to minimize the loss. We cannot completely eliminate the loss. Okay. So coming to the latest code. So now I will be discussing on the various CODAL provisions based on IS 1893 2016 version. So we all know that the main concept was derived from 2002 code. So whenever we will learn the 2016 version code, we have to just go through the 2002 version also. So we have the dynamic analysis and simplified method or direct method. This dynamic analysis is more realistic approach. It is more critical and it is more realistic approach compared to the less tedious or easy method. So the less tedious or easy method is the lateral force procedure method, or it is also known as equivalent static analysis method or equivalent static force method. So these three methods are basically the same method. Okay, so it is basically a ready-made method. The dynamic analysis, under this we have time history and response spectra method. We have Rayleigh method also, which is basically focused on the older recordings or older data. That means what are the various earthquake data we have obtained. And this direct method is a very simplified method. This method is basically taught in undergraduate or postgraduate programs. So if we come to this method, this lateral or equivalent static method, it is mentioned in clause 7.6 of IS 1893. So, and in the dynamic analysis, they are mentioned in clause 7.7. So, as I told you, this dynamic analysis, we have response spectra method, modal time history method, and time history method. Another method which is not mentioned in our code, which is mentioned in the foreign code like FEMA, Federal Emergency Agency, FEMA 356. In this code given by the US corporation, in that code we have a mention of pushover analysis. Pushover analysis is basically a static analysis, but inelastic static analysis. Okay. So this is also a performance-based method. So coming to the equivalent static analysis according to the 2002 and 2016 version. So first of all, what we have to find out? So these earthquake forces, they are transmitted throughout all the floors of the structure. At every floor, this total load is distributed among themselves based on certain formula. So before that, the first step is to find out the natural time period. The natural time period with which the structure is vibrating. So this time period may be different for different structures. It can be defined for RCC. This time period formula can be defined for steel structures like that. Now, this is a formula that is time period is 0.09 H divided by root D, where the structure is containing infill walls. That means we have partition wall as well as we have exterior walls. This is the realistic approach. That is 0.09 H. H means the height of the building divided by root D. Root D is the dimensional length, the length along the dimension. That is, it can mean X direction. So we will take the plan of the building and we will measure along X direction how much it is the length. And for Z direction also, we will calculate how much is the length in the Z direction. So basically, we will have two natural time periods. That is Tx along in X direction and Tz along in Z direction. So minimum of these two time period will be considered. So everything is given. So similarly, after this, calculating the natural time period, we will calculate the design horizontal seismic coefficient. It is a parameter or it is a coefficient which is based on all these parameters, where Z is the zone factor. Zone factor, as I told you, it is a value based on zone 2, 3, 4, and 5. I represents importance factor. SA by G is basically the response spectra coefficient. R is response reduction factor. So all these values of Z, I, SA by G, and R, all these, they are given in various tables of this IS code. So as I told you, Z seismic factor, all this, the various representation is also already given in the slide. Now coming to this, actually the snap, the picture, or this is the CODAL provision given in the code. It is given in clause number 6.4. Now, if you talk about the Z seismic zone factor, it is given in table 3. Importance factor is given in, we have something value like 1.5 for critical and lifeline structure, that is more important structures, 1.2 for business structures, and 1 for rest. Similarly, that means we have the response reduction factor also given. SA by G is the design acceleration coefficient. So this design acceleration coefficient, it is a certain parameter which is dependent on the type of soil as well as natural time period. So see here, SA by G, the design acceleration coefficient is dependent. We have rocky or hard soil. We have medium or medium stiff soil. Also, we have soft soil. So based on the value of this time period T and based on the value of time period T and the type of soil, we can select the value of SA by G. Okay. Now we will check what type of soil is it. Now if we design a model structure which is in Kolkata, we have to go for soft soil. If we have to design for a building in Darjeeling, it is rocky soil. Now coming, so this is the SA by G, this is the graph. It is basically the plot which is basically obtained from for type 1, type 2 and type 3 soil. So basically it is a pattern, it's a graph for response spectra, but we don't mainly need this graph. Pardon, yes.
Saira, please mute yourself.
Yes,
Saira,
ma'am.
please mute yourself.
Yes, ma'am.
Sorry, ma'am.
Person with the name Saira, please mute yourself. You can carry on, Saurabh.
Okay. So coming to the damping ratio, zeta. So the damping ratio is basically it's a value which is dependent on the type of structure. For RCC structure, the damping ratio is 5%, which is given in the code of 0.05 value, while the damping ratio for steel is 0.02, that is 2%. For RCC, it's 5% and for steel is 2%. Now, this is the importance factor. The importance factor, we usually take 1.5. We take all the buildings as important buildings, whether it is commercial or whether it is residential or whether it is institutional. So coming to the response reduction factor, this R value is dependent on the type of moment resisting frame. So the moment resisting frame is basically dependent on ordinary moment resisting frame and special moment resisting frame, SMRF. So this OMRF and SMRF we have, so initially in the 2002 version code, it was the values were very much less specific. But in this table 9, in the 2016 version code, we have a lot of data, a lot of values given. So basically, if we talk about OMRF, OMRF is basically the ordinary moment resisting frame or the frame structure which is designed according to IS 456-2000 code, the normal RCC code. If we talk about SMRF, for SMRF structure, we have to consult the ductile detailing code, that is IS 13920. IS 13920 is also have been advanced. Earlier it was 1993 code, now it is 2019 code again. Okay, so usually we will take for, if we develop an RC structure, we have to go for RC buildings. If you go for steel structures with bracings or without bracings, then based on the modeling, based on the structure they're modeling, we have to take that value. Coming to the percentage of live load we have to take. It is a very important point of concern that how much live load we have to consider. Normally, for normal designing, the elastic designing according to our RCC code, whatever the live load is coming, we have to take it. But whenever we are talking about seismic load, if the live load is up to 3%, up to and including 3%, 3 kilonewton per meter square, if the live load value is within the range of 3 kilonewton per meter square, then the percentage of live load will take 25%. But if it is more than 3, then you have to take 50%. So after getting all the values of these values, that is the seismic zone factor, response acceleration coefficient, response reduction factor, and importance factor, taking all these values from the table, we have to calculate this and we will get this seismic coefficient. Now, using the seismic coefficient, we have to calculate the design base shear VB. The total design base shear or seismic base shear VB is calculated as AH multiplied by W. So what is this W? This W represents the cumulative of the seismic load. That means for every story, for every floor, we have to calculate the weight of the floors. That is the weight of floors considered means the weight of the column, slabs, buildings, all the structural elements. And we have to make it, we have to take the cumulative of all the seismic loads. That is the W. So the design base shear is this equation. And after that, based on design base shear, we have to find out the lateral forces. That means how much forces is distributed among all the floors. How much forces is distributed among the floors. So if we see, QI represents the design lateral forces or the lateral forces acting on each and every individual floor level. Seismic weight we can see at different ith floor, that means at respective floor, if it is I is 1 first floor, I is 2 second floor, like this. So, after calculating the design base shear, we will calculate the lateral forces acting on the structure. And after that, we have to plot the variation. We have to plot the variation of base shear as well as lateral forces acting on the structure. And we have to check what is the pattern or the pattern of the graph. And a very important point to be considered, that is, if we talk about whenever we do static analysis, we also have to consider the dynamic analysis also. Because if we have two types of analysis side by side, it will be easy for us to compare and study. So according to this, the 2016 version, dynamic analysis should be conducted on all types of buildings except the buildings having less than 15 meters and also which is located in seismic zone 2. Okay, so that means in the revised code, they have told us that we have to consider the dynamic analysis of any structure having building height more than 15 meters. Now, this is a sample problem I've taken. I've brought this up for all of you, that this was the plan of a school building which was extremely got dilapidated or collapsed due to this huge earthquake. So what have they done? Say this plan, and taking this plan after this earthquake took place, the seismic study was considered. So it was considering it was like G+5. So we have the plinth level 1 meter and all the floors are 3 meters. It's like corridor shape. The school building is very small school building. It is somewhat very much rectangular in plan. So based on this equivalent static analysis, in each and every floor, we can see that the lateral forces have been calculated at the ground level, at the first floor, second floor, third floor, fourth floor, and roof level. We can see the lateral forces have been calculated using this elastic or static analysis method. And also the design base shear. What is design base shear? Design base shear will be something like cumulative of all this. That means in the first floor it is 11,1103 kilonewton. In the second for the fourth floor, it will be added up. So from top floor to the ground floor, the forces will be added up. So this is how the base shear is calculated. So these two columns are most important. So now the last part is that we have to plot the graph. So as I told you, so this is the values we have got. We can see at the all in respective floor levels, whatever the values we have got, this has been mentioned here. So at the ground level, we have 53 kilonewton. At the first floor level is 218. Second floor level 494. Third floor like this. So similarly, as we go from ground level, from the base level to the roof level, the lateral forces increases. And we can see a parabolic variation is obtained based on this lateral force distribution. This is called lateral force distribution. Another method is the dynamic analysis. Dynamic analysis, it is also, this response spectra is also slightly less complicated compared to time history. It takes into the picture of MDOF system, that is multiple degrees of freedom. So this also has been obtained from, this is basically modal analysis. We consider the various mode shape of the structure, which is subject to earthquake, and we find out. So this is one paper which which was published in the year 2021. I did the seismic analysis on irregular plan buildings. Irregular plan buildings I will show you, which is not regular plan, which is not rectangular, but the plan is somewhat like H shape or T shape or L shape like this. So it was published in Springer, the journal, in the last year. And I will show you that all these data we have to take. We have taken what amount of live load we have to consider. We have to consider the dimensions of the columns, beams, and slabs. And this was our elevation. And so the first was what I did. This was a paper work was done by my undergraduate student, a group of 10 students. So we considered 25-story U-shaped building. We can see the plan as well as elevation. I have taken T-shaped or X-shaped building, L-shaped building, and inverted T-shaped building. So we can see that if we talk about the results, so we can see that basically our motto was to study the impact of this irregularity in plan. But so what will be in which case the earthquake load or the earthquake effect will be hazardous? U, X, L, and inverted T. So we did the equivalent static analysis, and this was the graph representing the maximum floor displacement or the rooftop displacement compared with the floor height. As we know, as we move from base to the topmost height or the topmost roof level, the floor displacement or rooftop displacement increases because the lateral force is increasing. Hence, the story drift or the floor displacement will be increasing. As we can see this pattern, that is the first floor was 4.5 meter compared to the ground level. Then, so as we move from the ground to the top level, the floor displacement increases. So this was for U-shaped plan building. Similarly, for X-shape, the floor height, the displacement was around 22 millimeters. For U, it was between 16 to 18 millimeter. For X-shape, it was 20 to 25 millimeter. For L-shape, it was something like very huge. It was a huge, we saw around 700 millimeters of story displacement. For inverted T-shape, it was around 140 to 160 millimeter. So we considered and we did all the comparative study, and we found out that the most hazardous and most disastrous effect takes place on L-shaped structure and X-shaped structure. So whenever we have to plan any building which is X-shaped plan or L-shaped plan, we have to take into consideration of the hazardous effect, as well as we have to properly design and construct the shear work. So this is everything regarding today's session. So if anyone have any questions, he or she may ask. Any questions?
Saurabh,
So if,
sorry. Yes, carry on. Whoever was asking.
yes, if anyone have any question, please ask.
So Saurabh, would you elaborate to the people listening to your seminar, webinar, about what are the control systems? I just, you can just talk about a little bit about that. What are the control system for this counterbalancing the forces that are there for the earthquake? In tall buildings, where we are talking with regards to tall buildings. So what are they adopting to?
Coming to the remedial solutions or the control systems, either we have to, first of all, one type of the solution is that the construction of shear wall. Very much important. We have to construct the RCC shear wall. It can be in box shape, it can be L shape, it can be rectangular casing, a minimum of about 125 to 150 mm thickness. Another type of control system, we can use bracings. Along, if you talk about RCC structure, since my research was mainly focused on RCC structure, we can use cross bracings, steel cross bracings or RCC bracings to minimize the effect of earthquake. It can be V-shaped, it can be X-shaped. Then we can also go for some special reinforcement detailing. That means we have to provide a special stirrupping, we have to provide special hooks, we have to enhance the reinforcement quantity at the beam column joints. So there is a lot of remedial measures which can be taken place in order to minimize the earthquake hazard. Even nowadays, we are going for base isolation, a very popular technique nowadays, vibrational base isolation techniques like dampers, which is very much used in the construction of some hospital building in Taiwan and in Shanghai also. So the Chinese constructors, they are very much using this concept of, even in Japan also, this base isolation is very much in practice nowadays.
Yeah, thank you so much. If the students have any questions, they can put it over there.
Excuse me, sir. This is Moinuddin Sheikh, and hello,
Yes, please ask. Yes, please ask.
sir. Have you study any effect of composite construction in seismic? The one you are talking, especially the U-shaped building. Okay, so let's say instead of putting CRL and all those, if we go for composite construction, that is a combination of steel, standard steel hollow standard sections with the RCC, that is the composite constructions. So sir, have you studied the effect of composite construction in your analysis and study?
one of the research papers I have done that is based on shear wall. Another group of students, they published a paper. So I have not presented this in the PPT. I have regarding the composite construction. Yes, I think whenever we're talking about earthquake resistant structures, the RCC and steel both should be, composite construction is still in my research scope. I will be dwelling, or I will be focusing more on composite construction now. That means the core of the building will be something like RCC. The inner core will be steel structure, and also the outer periphery should be we will put cross bracings like this. The composite construction I have not till now I have not done any research on this.
Okay, sir. Thank you.
Okay, thank you. If anyone want to ask any question, please ask. Then we will end the session. So, okay, so thank you all for participating, and Professor Saurabh Kaur. So
Yes,
thank you all.
I thank you everyone. I thank you the total TECHNO India family for organizing such wonderful webinar. Thank you everyone. Thank you.
Okay, thank you. Okay, thank you all. So we are ending. Okay, please stop the recording from your side. Okay.